All right, let's dive into today's cybersecurity headlines. Fresh from Security Archive, a whole stack of research, all published today, March 18th, 2025. Ready to unpack it all.
Yeah, looks like we've got a pretty intense mix here. A lot on AI and machine learning, some interesting developments in privacy tech, and of course, the never-ending evolution of cryptography.
So where do we even begin with all of this? It's a lot to process, even for us.
Well, I think the biggest theme I'm seeing is this sort of erosion of trust in machine learning. A lot of today's papers are pointing to vulnerabilities that go way beyond just your typical software bugs. It seems like there are some fundamental weaknesses in how we're training and using these models.
Okay, so let's start with that. One paper in particular caught my eye. Trust Under Siege. Labels spoofing attacks against machine learning for Android malware detection. That title doesn't exactly inspire confidence, does it?
Not really. It's a pretty unsettling read, honestly. The researchers have found this new attack vector. They're calling it label spoofing. Basically, attackers can embed these tiny, almost undetectable malicious patterns into completely benign Android apps.
And that causes...
It tricks the antivirus engines, the ones that are supposed to be labeling data for training these machine learning-based malware detectors. So these safe apps are misclassified as dangerous.
I see where this is going. Poison data, right?
Exactly. And even a small contamination, like 1% of poison samples, can lead to a complete denial of service. And it's not just theoretical. They actually showed that they could target specific benign apps, potentially ruining their reputation by tweaking a tiny fraction, like 0.015% of the training data.
That's wild. So basically, even if a company is relying on these advanced malware detectors, their entire system could be compromised by a really subtle attack.
And what's even worse, standard anomaly detection techniques might not even pick up on this kind of poisoning. It's like a stealth attack on the very foundation of the system.
Scary stuff. And it seems like this problem of trusting training data comes up in another paper too. BLIA, detect model memorization in binary classification model through passive label inference attack. What's going on there?
So this one gets into this issue of label memorization. They found that even when you use privacy-enhancing techniques like label differential privacy or label DP, attackers can still figure out the original training labels just by looking at the model's output.
So even if you try to anonymize the data used to train these models, the model itself can leak information through its predictions.
Yeah, that's the gist of it. They actually tested this by intentionally flipping the labels on a few data points during training. Even with label DP, their attacks could still identify those flip labels with a pretty high success rate.
Wow. So it's like no matter how hard you try to hide the data, the model itself might remember it. Kind of defeats the purpose of privacy measures, doesn't it?
It really does. It suggests that just masking or adding noise to the data might not be enough. We need to think about how the model itself is leaking information.
Definitely food for thought. Now, the last paper on this topic of machine learning vulnerabilities is poison source code detection in code models. Is this more bad news?
Actually, this one's a bit more optimistic. It focuses on detecting poison code samples in the training data used for code analysis models. They've developed this new model called Code Garrison, or CG, which seems to be pretty good at spotting these malicious samples.
So a bit of a silver lining. While some research highlights the vulnerabilities, this one offers a potential solution, at least in the context of source code analysis.
Right. It's a good reminder that while the attackers are getting smarter, so are the defenders. It's a constant back and forth.
Now, shifting gears a bit, AI isn't just a target, it's also becoming a weapon in itself. Several papers today are really highlighting this dual nature of AI in cybersecurity.
It's a huge concern. The more powerful AI models become, the more dangerous they are in the wrong hands. Today's research is really digging into both how to protect AI systems from attack and how to understand the offensive capabilities that AI might enable.
One paper that takes this on directly is a framework for evaluating emerging cyber attack capabilities of AI. Sounds pretty comprehensive.
It is. They're proposing a structured way to evaluate how advanced AI models could be used in attacks. What I found interesting is that they analyzed over 12,000 real-world attempts to use AI for malicious purposes.
So this isn't just hypothetical, they're looking at actual attacks.
Yeah, and that analysis helped them identify these key patterns in how AI is being weaponized. They even created a benchmark of 50 new challenges to specifically test AI's offensive capabilities.
So basically, they're trying to understand the enemy's tactics by seeing how AI can be used for bad.
Exactly. By understanding the potential threats, we can start to develop effective defenses.
Makes sense. Another paper, Multi-Agent Systems Execute Arbitrary Malicious Code, explores the vulnerabilities of multi-agent AI systems.
This one is a bit alarming. It shows that even if individual AI agents are secure, malicious content can hijack the communication between them, leading to some pretty bad outcomes.
Like what?
Think arbitrary code execution, data exfiltration, basically taking control of the entire system. And what's scary is that these attacks can work even if the individual agents aren't vulnerable to things like prompt injection. It's the interaction between them that creates the weakness.
That's a whole other level of complexity. It's not just about securing a single AI anymore. It's about securing the entire network.
Absolutely. And speaking of complex interactions, we've also got two new papers on the ever-popular topic of jailbreaking large language models, making every step effective. Jailbreaking large vision language models through hierarchical KV equalization and siege, autonomous multi-turn jailbreaking of large language models with tree search.
So the battle to keep these powerful language models under control continues. What are these new jailbreaking techniques all about?
Well, the first one, HKVE, is all about efficiency. It introduces a way to generate adversarial prompts that can bypass safety filters, and it does it using fewer resources than previous methods.
So it's basically a faster, more efficient way to jailbreak these models.
Pretty much. And then we have Siege, which focuses on multi-turn conversations. The idea here is that an LLM safety can actually degrade over time as you interact with it.
So the longer you talk to it, the more likely you are to find a way to break it.
That seems to be the case. By tracking policy violations and re-injecting them into the conversation, Siege can jailbreak models like GPT 3.5 and GPT 4 in surprisingly few turns.
It's a constant arms race, isn't it? As soon as we find a way to secure these models, someone figures out a new way to break them.
And that brings us to another important theme in today's research: privacy, particularly in the context of decentralized and collaborative systems. We've got a whole bunch of papers on federated learning and blockchain technology.
Yeah, it seems like there's a big push to develop systems that can work together without compromising privacy.
Right. Collaboration is becoming more important than ever, but so is protecting sensitive data. One paper that caught my eye is Local Pan Privacy for Federated Analytics. It tackles this problem of maintaining privacy when individual devices in a federated learning system are repeatedly compromised.
Okay, so a pretty high security scenario. What did they find?
They found that there's a bit of a fundamental trade-off here. You can't have perfect privacy under repeated intrusion and still collect useful data. But they do propose a solution using standard cryptographic primitives, which is a step in the right direction.
So it's not a perfect solution, but it's progress.
Exactly. And then we have Preamble, private and efficient aggregation of block-sparse vectors and applications. This one's all about making secure aggregation and federated learning more efficient.
Efficiency is always a good thing. What's their approach?
They've introduced a new mechanism that works really well for high-dimensional block-sparse vectors. This is important because those kinds of vectors are common in federated learning when you're dealing with large model updates.
So this could make federated learning much more practical for real-world applications.
That's the idea. And then there's research on large language model, cross-cloud privacy protection, and collaborative training based on federated learning, which tackles the specific problem of training large language models across multiple cloud providers while keeping things private.
Cross-cloud training sounds complicated enough, let alone adding privacy concerns on top of that.
It is, but they've developed a pretty comprehensive framework that integrates cryptography, dynamic model aggregation, and data harmonization. It seems to be a promising approach, at least based on their results.
Sounds like they're really trying to cover all the bases.
They are. And then we have zero-knowledge proof-based consensus for blockchain-secured federated learning. This one combines blockchain technology with federated learning.
Okay, that's a lot of buzzwords in one title. What's the point of combining those two things?
So they're proposing a new consensus mechanism that uses zero-knowledge proofs to validate contributions in a blockchain-secured federated learning system. The idea is to improve both the privacy and efficiency of the system while also making it more resistant to attacks.
Interesting. So it's like taking the best of both worlds, blockchain and federated learning, and combining them into a more secure and efficient system.
Right. And last but not least, we have FedSDP, explainable differential privacy in federated learning via shapely values. This one aims to make differential privacy in federated learning more transparent and understandable.
Transparency is always good, especially when it comes to privacy. How do they do that?
They use Shapley values, which is a concept from game theory, to measure the privacy contribution of each local training update. This allows them to adjust the level of noise injection more dynamically, achieving a better balance between privacy and model performance.
So basically it gives you more control over the privacy utility trade-off, and it helps you understand what's going on under the hood.
Exactly. And that's a really important step in making these privacy-preserving techniques more trustworthy and usable in the real world.
All right, so we've talked about vulnerabilities in machine learning and the growing concerns around AI as a weapon. We've also looked at some promising research on privacy in federated learning and blockchain systems. Now, what about the attack and defense landscape beyond those areas?
Well, as always, there is a constant back and forth between attackers finding new weaknesses and defenders developing new ways to protect our systems. One paper that highlights this dynamic is Enhancing Resiliency of Sketch-Based Security via LSB Sharing-Based Dynamic Late Merging. It focuses on securing sketch data structures, which are widely used in network traffic monitoring.
Okay, so pretty fundamental stuff. What's the vulnerability they found?
They discovered a new attack that can target the small counters used in these sketch data structures. To address this, they've developed a new Siamese counter design that's much more resilient to these attacks.
So basically strengthening the foundation of these security systems.
Right. Then we have Scoop, cost-effective congestion attacks in payment channel networks. This one focuses on disrupting payment channel networks, which are becoming increasingly popular.
So another attack targeting a specific type of system. What's COOP all about?
It's a framework for launching two new types of congestion attacks on payment channel networks. These attacks are formulated as linear optimization problems and take into account both the capacity and length of payment paths within the network.
So they've really thought this through.
They have. And their simulations show that these attacks are more effective and efficient than previous methods, which is concerning.
Definitely something to keep an eye on. But, of course, it's not all doom and gloom. We also have some interesting new defense strategies. Defense against model stealing, based on account-aware distribution discrepancy, proposes a new way to protect trained machine learning models from being stolen.
Yeah, this one's pretty clever. They've developed a non-parametric detector called ADD that can identify malicious users who are trying to steal a model by analyzing their query patterns.
So basically catching the thieves red-handed.
Pretty much. And by combining this with prediction poisoning techniques, they can make it even harder for attackers to steal the model.
That's a nice one-two punch. And then we have Mirror Guard, adaptive defense against jailbreaks via entropy-guided mirror crafting. This one takes a different approach to defending against jailbreaking attacks on LLMs.
It uses this idea of creating mirror prompts that are structurally similar to the input, but designed to be safe. By comparing the original prompt and its mirror, they can detect and mitigate risky inputs.
So it's like a safety net for these language models.
That's a good way to put it. And then there's proactive adversarial defense, harnessing prompt tuning in vision language models to detect unseen backdoor images. This one tackles the problem of backdoor attacks in vision language models.
Backdoor attacks are tricky. They can be hard to detect.
They are. But this method uses prompt tuning to train the model to distinguish between clean images and those containing hidden backdoors, even if the backdoor trigger is something the model hasn't seen before.
So a more proactive approach to defense.
Exactly. And finally, we have Mind the Gap, detecting black box adversarial attacks in the making through query update analysis. This one focuses on detecting black box adversarial attacks as they're being generated.
Catching them in the act, so to speak.
Exactly. They do this by analyzing the similarity of input updates during the attack process and have developed a new metric called delta similarity to help them do this.
Wow, that's a lot of new defense strategies. It's encouraging to see researchers coming up with innovative solutions to these complex threats. Now let's shift our focus to quantum computing and cryptography. This is an area that's becoming increasingly important as quantum computers become more powerful.
Definitely. The potential for quantum computers to break existing cryptographic algorithms is a huge concern, and a lot of research is going into developing quantum-resistant cryptography.
One paper that dives into this is Implementation of Classical Client Universal Blind Quantum Computation with 8-State RSP in Current Architecture. It sounds pretty technical, but what's the main idea?
Basically, it's about how a classical computer can securely delegate quantum computations to a quantum server. They propose a specific implementation that uses current quantum computing architectures and combines blind quantum computation with remote state preparation techniques.
So it's like outsourcing your quantum computing needs, but doing it in a way that protects your data.
Exactly. Then we have Tetris Lock, quantum circuit split compilation with interlocking patterns. This one focuses on protecting intellectual property in quantum circuits.
That's an interesting problem. How do you protect IP in the world of quantum computing?
They propose a method for obfuscating quantum circuits using a technique called split compilation with interlocking patterns. This makes it much harder to reverse engineer the circuits without significantly impacting their performance.
So it's like adding a layer of security to the circuits themselves.
Right. And then we have a very timely paper, Performance Analysis and Industry Deployment of Post-Quantum Cryptography Algorithms. This one looks at the practical challenges of transitioning to cryptography that can withstand quantum attacks.
So this is about making sure our systems are ready for the quantum future.
Exactly. They analyzed the performance of two standardized post-quantum cryptography algorithms, Crystal's Kyber and Crystal's Dilithium, and discussed the challenges of deploying them in real-world systems.
It sounds like a complex undertaking.
It is, but it's essential. And lastly, we have linearly homomorphic signature with tight security on lattice. This paper introduces a new cryptographic scheme based on mathematical lattices.
Lattices, that's getting into some pretty advanced math.
It is, but lattice-based cryptography is a promising candidate for post-quantum security. This new scheme has some advantages over existing lattice-based schemes in terms of key size, signature length, and computational cost.
So it's a step forward in the quest for quantum-resistant cryptography. Now, beyond federated learning, what other privacy-preserving techniques are researchers exploring?
Well, privacy is a concern in many different domains. One paper we already touched on, Practical Implications of Implementing Local Differential Privacy for Smart Grids, dives into the challenges of protecting electricity consumption data.
Smart grids are a great example of how data privacy concerns are becoming increasingly relevant in everyday life.
They are, and this paper explores the different trade-offs involved in implementing local differential privacy in this context.
Then we have safeguarding LLM embeddings in end-cloud collaboration via entropy-driven perturbation. This one's all about protecting text embeddings in collaborative language model applications.
They've developed a method called EntroGuard that adds carefully crafted noise to the embeddings to make them harder to reverse engineer. This protects the privacy of the underlying text data without sacrificing accuracy.
So it's like adding a privacy shield to these language models.
Exactly. And then there's TFHE Coder, evaluating LLM agentic fully homomorphic encryption code generation, which explores the use of large language models to generate code that uses fully homomorphic encryption.
Fully homomorphic encryption, that's the holy grail of cryptography, right? Computing on encrypted data without ever decrypting it.
It is, and this research shows that LLMs, with some help from retrieval augmented generation and few-shot prompting, can be used to generate usable FHE code.
So another example of how AI is being used to advance cryptography.
Absolutely. Then we have Marcia, safeguarding data confidentiality and blockchain-driven process execution. This one combines attribute-based encryption, distributed storage, and blockchain technology to provide fine-grained access control to data on the blockchain.
So enhancing the privacy features of blockchain systems.
Right. And then there's noise-aware, differentially private variational inference. This one proposes a new method for performing approximate Bayesian inference while accounting for the noise introduced by differential privacy.
So making sure the noise added for privacy doesn't mess up the statistical analysis.
Exactly. And finally, privacy bills of materials, a transparent privacy information inventory for collaborative privacy notice generation in mobile app development, takes a more practical approach to improving privacy notices in mobile apps.
So making sure users actually understand what data is being collected and how it's being used.
That's the goal. Now let's talk about watermarking. This is a technique that's used for both security and copyright protection. We've got several papers today exploring new watermarking techniques.
Yeah, watermarking is a fascinating area. It's like embedding a hidden message in the data itself.
Exactly. One paper, SEAL, Semantic-Aware Image Watermarking, introduces a method that embeds semantic information about an image directly into the watermark. This makes the watermark more robust against tampering and forgery.
So it's not just a random pattern. It actually carries meaning about the image.
Right. Then we have robust watermarking using generative priors against image editing, from benchmarking to advances. This one introduces a new benchmark for evaluating watermarking robustness and also proposes a new watermarking technique called Vine that uses generative models to improve robustness.
So they're really pushing the boundaries of what's possible with watermarking.
They are. And then there's GuardSplat, efficient and robust watermarking for 3D Gaussian splatting, which focuses on watermarking 3D assets.
3D watermarking, that's pretty cool.
It is. They've developed a framework that can embed watermarks into 3D assets represented using Gaussian splatting, which is a popular technique for representing 3D scenes.
So extending watermarking to a whole new dimension, literally.
Exactly. And then we have permute and flip, an optimally stable and watermarkable decoder for LLMs. This one proposes a new decoding method for LLMs that's specifically designed to be watermarked.
So adding watermarking capabilities to the language models themselves?
Right. And finally, mark your LLM. Detecting the misuse of open-source large language models via watermarking explores the use of watermarking to detect misuse of open-source LLMs.
So it's like a way to track how these models are being used and make sure they're not being used for malicious purposes.
Exactly. Now let's touch on supply chain security. This is a critical area that underpins the security of all software, and it's been the target of some high-profile attacks in recent years.
Yeah, supply chain attacks can be devastating because they can compromise software at its source. One paper that analyzes these attacks is Closing the Chain: How to Reduce Your Risk of Being SolarWinds, Log4j, or XEUtils.
They look at the specific techniques used in those attacks and map them to tasks in standard supply chain security frameworks. What's interesting is that they found gaps in those frameworks, suggesting that even full compliance might not be enough to prevent these attacks.
So there's always room for improvement, even well-established security practices.
Absolutely. And finally, let's talk about some of the domain-specific security challenges that came up in today's research. There's a lot of interesting work going on in areas like virtual reality, hardware design, and cryptocurrency.
One paper that caught my attention was Securing Virtual Reality Experiences: Unveiling and Tackling Cybersickness Attacks with Explainable AI. Cybersickness attacks, that's a new one for me.
It's a new type of attack that targets cybersickness detection models in VR environments. By fooling these models, attackers can cause users to experience discomfort or nausea.
That's pretty insidious.
It is, and the paper also proposes a framework for detecting these attacks using explainable AI, which helps to understand why the attack is working and how to design more resilient systems.
So bringing AI to bear on the problem, both offensively and defensively.
Exactly. Then we have Veriliki, navigating IP protection versus utility and fine-tuning for LLM-driven Verilog coding. This one looks at the challenge of protecting intellectual property when using LLMs to generate Verilog code for hardware design.
Hardware design is a sensitive area. A lot of valuable IP there.
It is, and they show that IP can leak through the fine-tuning process, highlighting the need for better protection mechanisms.
Neon Pool: Reimagining cryptocurrency transaction pools for lightweight clients and IoT devices, focuses on making cryptocurrency more accessible to resource-constrained devices.
They've developed an optimized transaction pool that uses Bloom filters to reduce the memory footprint, making it suitable for lightweight clients and IoT devices.
So making crypto more efficient and scalable.
Right. And then there's enabling high-frequency trading with near-instant, trustless cross-chain transactions via pre-signing adapter signatures. This one proposes a protocol to speed up transactions between different blockchains, potentially enabling high-frequency trading and decentralized finance.
So making crypto more responsive and interconnected.
Exactly. And then we have Bitcoin Battle, burning Bitcoin for geopolitical fun and profit. This one analyzes real-world Bitcoin misuse by nation-state actors.
So a real-world case study of how crypto can be used for nefarious purposes.
It is, and it highlights the challenges of tracking and preventing this kind of activity.
Then there's a bubble cluster federated learning framework for privacy-preserving demand forecasting on heterogeneous retail data. This one applies federated learning to the problem of sales prediction in the retail industry.
They've developed a framework that groups retailers into bubbles based on their data characteristics, which improves accuracy while also protecting privacy.
So another example of how federated learning is being applied to real-world problems.
Absolutely. And then there's electromagnetic side-channel analysis of present lightweight cipher. This one investigates the security of a lightweight cryptographic algorithm commonly used in IoT devices.
IoT security is so important, those devices are everywhere.
They are. And this research shows that the present cipher is vulnerable to electromagnetic side-channel attacks, which could allow attackers to steal encryption keys.
So another reminder that even lightweight cryptography needs to be robust.
Absolutely. And then there's From ML to LLM, evaluating the robustness of phishing web page detection models against adversarial attacks. This one tests the resilience of various phishing detection models against adversarial examples.
Phishing is such a persistent threat, and it seems like the attackers are always one step ahead.
They often are. But this research shows that while both traditional ML-based models and LM-based models are vulnerable, the LLM-based models tend to be more resilient.
So LLMs might be the key to building more robust phishing detection systems.
They could be. And finally, we have revisiting backdoor attacks on time series classification in the frequency domain. This one introduces a new backdoor attack method for time series data called freakback that's more effective than previous methods.
So another example of how attackers are constantly innovating and finding new ways to exploit vulnerabilities.
It's a never-ending battle, but the good news is that researchers are also constantly innovating and developing new defenses. It's an exciting and challenging field to be in.
Wow, we covered a lot today. From AI vulnerabilities to new privacy-preserving techniques to the latest developments in quantum cryptography, it's clear that the cybersecurity landscape is constantly evolving.
It certainly is, and staying on top of these developments is more important than ever. Thanks for having me on the show today. It was great to discuss all this with you.
Thanks for joining me. And to all our listeners, thanks for tuning in. Stay safe out there in the digital world.